Swayam Prabha. Digital India. Educated India.
Welcome to week 5, lecture 1 of our course on Muffler acoustics. So, we will begin lecture 5. So, if you recall, what we did in the immediately preceding lecture was we stopped at the transmission loss expression for a simple expansion chamber, which is shown here. So, we were just beginning to analyze the salient or the important features of the transmission loss spectra. So, our primary job in this lecture will be to discuss in greater detail about the transmission loss performance, the curves, and possibly about the sequential connections of the muffler elements. So, let us begin today's lecture. So, we have got a simple expansion chamber. By now you would have understood what do you mean by a simple expansion chamber, which is something like this. The flow comes in here, it goes out, and you have your this thing here. Now, as we saw from the last lecture, the transmission loss analysis was given by, finally it was given by T L is equal to 10 times log the base 10 and 1 plus 1 by 4 m minus 1 by m whole square sine square k naught L, and this is what we get. So, and what was m, where m was d by d square, d naught or capital D naught by small d naught whole square, okay. And k naught L is the Helmholtz number of the non-dimensional frequency, non-dimensionalized with respect to the chamber length L. So, this was your d naught and this was this. So, as we can clearly see from the expression here, when is the transmission loss maximum and when it is minimum. So, clearly it is a function of frequency, which is represented by the sinusoidal square of the sinusoidal function. So, when TL when TL is maximum, then of course, this circle term must be unity, that is 1. So, now under such a situation we can just put it 1 and simplify it further. So, we get this thing. Let me just get rid of this m thing. So, when does this happen? When sine k naught L is equal to 1 is equal to sine of 2n minus 1 or 2n plus 1 to pi by 2, where n starts from 0, 1, 2, 3, 4. So, let us simplify the expression k naught L is equal to 2n plus 1 pi by 2 for crest or domes. So, if you recall, our transmission loss spectra looked like this. So, it was like this. On the x axis is your Helmholtz number or the non-dimensional frequency, and this is your T L in dB. So, by this expression we mean that the maxima is occurring at the first frequency of occurring is k naught L is equal to pi by 2. So, when you simplify this thing further, you get C naught by 4 L. So, this is the frequency at which domes occur. So, this is the frequency at which your maxima occurs. What is the next frequency? When you set n is equal to 1, 2, 3, 4 like this. So, for the next frequency you get it will be just 3 times, that is let me call this as Fn. So, it will just be obtained by putting 2n plus 1. So, 2n plus 1 times C naught. So, where n is equal to 0, that is your first thing, you get C naught by 4L. So, that is where the frequency or the occurrence of the first dome, that is this one, occurs. Where n is equal to 1, then F becomes 3 C naught by 4L. So, this will correspond to this particular frequency where we circled. Where n is equal to 2, it will be 5 C naught by 4L. So, that will be this one. So, like this pattern keeps on occurring, but what is more important to us and to all acoustic designers, for a muffler designer, is basically where the trough occurs. So, where does the trough occur? Trough means, by what do you mean by a trough? By trough we mean where the transmission loss is 0 or it is probably a minimum, so that almost all the acoustic power goes away. So, now let us look at this figure. Now, if you look at the transmission loss graph, wherever this, let me use a different color, maybe purple. So, wherever this trough is occurring, that is characterized by a 0 transmission loss. So, then at such a frequency TL is 0. So, when does that happen? Clearly, if you look at the transmission loss expression in the last lecture, when sin k naught L, when this is equal to 0, you have this entire term goes away when sin k naught L is 0. Then you are just left with log of 1 and obviously 10. So, this will become 0. So, this will happen when sin k naught L is equal to sine of n pi. So, let us simplify this thing. So, k naught L is equal to n pi. So, you get 2 pi f by c naught times L is equal to n pi, pi is cancelled, and f trough occurs at n c naught by 2L, n c naught by 2L, where n is equal to 1, 2, 3, n is equal to 0 will obviously be a trivial case, that is at 0 frequency. So, for non-zero frequency, when you put C naught by 2L, C naught by L, C naught by 3 times 2L and so on, you get the frequencies of trough. So, why is this trough important? Let us analyze this, because you see from the principles of anti-logarithmic addition, no matter if you are getting a very high transmission loss, very high attenuation at a certain frequency, but not such a good performance at other frequency range. So, and it so happens that most of the noise is concentrated in this frequency band and in here and so on. So, although you are getting good performance at other frequencies where the domes happen, but not so good performance at where the troughs occur obviously, and then unfortunately if the engine noise is concentrated in these frequency bands somewhere here, then your muffler is pretty much useless, because 0 transmission loss means all the acoustic power is going away, it is transmitted as it is. So, the muffler is transparent or is useless. So, by the principles of anti-logarithmic addition, if you add the noise reduction occurred somewhere here, here, everywhere, you will see that the net transmission loss that one would get over different frequency band is basically given by the frequency where least attenuation is produced. So, basically there is some kind of a bottlenecking or some kind of a limitation that is imposed by the trough, and this is especially important because automobiles are basically a variable speed drive, because the speed changes and the number RPM of the engine changes, and basically automobile engine exhaust noise is dominated by the first firing frequency and its multiples. So, if the speed changes, the firing frequency, the RPM of the engine changes and the firing frequency obviously changes. So, the idea is that the frequency spectrum keeps on changing based on different RPM, and for such a variable speed drive the noise spectrum continuously changes. So, what does one do to solve this problem? What does one do to basically design such a muffler that's effective for an automobile or exhaust engine noise which is running at different RPMs? So, one principle is to basically design, the idealistic situation would be to design a muffler which should produce a broadband transmission loss. So, this is the term that we are using perhaps for the first time let me write this in bold and in capital: broadband transmission loss, or also insertion loss, broadband, or also known as broadband performance. We keep hearing this term broadband performance or broadband attenuation in several contexts. In the context of mufflers, it means that the muffler is effective for a large range of frequencies, such that, well, if you are considering a complicated muffler and you are this is the TL and here is frequency and you are getting something like this kind of a curve, what it means is that, you know, beyond a certain frequency, beyond a low frequency region, the performance is really catching up, and for most of the frequencies you are guaranteed to get a constant, say maybe this is like 10 dB, this is, say maybe this is 10 dB line. So beyond a certain frequency you are guaranteed to get at least 10 dB of noise reduction, and there is no chance of muffler failing at any frequencies beyond this thing, because the transmission loss or the attenuation performance is never 0 beyond a certain frequency. So by ensuring a broadband performance of a muffler, we really are ensuring that there is no trough like what we saw in the graph presented here. Of course, simple expansion chamber, it is too simple to be used, but probably the most well studied element and probably the first element that we have studied in this course and all the courses in noise control engineering. A simple expansion chamber is always studied because it is analytically the simplest to understand, but it is not used in practice. Obviously, there are much more additions to it, like extensions and dissipative mufflers, slow reversals, and vertical perforates, bulk heads, and whatnot. So the point is that the point of introducing all the complicating features and more elements is to basically improve the performance with respect to a simple expansion chamber, that is your troughs. So the idea is to uplift the troughs or to increase the transmission loss performance for as wide frequency band as possible. So before we finish the discussion of TL analysis of a simple expansion chamber, I guess we probably would like to do some approximations to the TL expression that we obtained so far in terms of the area expansion ratio, as well as conduct some basic parametric studies which I will present you using MATLAB in a while to further understand how attenuation performance happens. And actually, incidentally, there is one more thing that I forgot to mention, sorry. So essentially a muffler, a simple expansion chamber muffler, what we are seeing here, it can be considered like a duct. Say if the length is closed at both ends and you have the acoustic pressure field here, well, I am just making use of the some space here to write down the acoustic pressure field here. It's something like this. If you recall our discussions, this is the expression for pressure. Velocity is nothing but minus, and you will have your characteristic impedance at the bottom denominator. So why am I telling you this? Because to get the resonance frequencies or the actual resonance frequencies of a simple expansion chamber, one needs to put a rigid wall condition at the left end and also the right hand. So basically, once you do that, you will get A is equal to B, and another condition that you are probably going to get is A is equal to B times e to the power 2 j k naught L. So once you substitute this in here, so instead of B I will write B, A I will write B here, making use of this expression, I will get rid of this, and what I probably would do is write 1 minus e to the power 2 j k naught L times B is equal to 0. B cannot be 0, but otherwise you will get a trivial solution. So this entire thing has to be 0. So once you simplify this thing further by multiplying by e to the power minus j k naught L, what are we going to get? Minus 2 j k naught L times minus. So this becomes C minus this, and C minus Js is equal to 0, isn't it? So then basically your cos will get cancelled. Eventually we left with nothing but sine of k naught L is equal to 0. Eventually you are going to get that, and this is your condition what we got from the transmission loss expression just a while back when we were dealing with the troughs, isn't it? So this discussion is important because the troughs always occur at the resonance frequency, first, second, third, fourth and so on, resonance frequencies of a simple expansion chamber. So, this is one point I thought of mentioning. And finally, before we end the discussion on TL analysis of such a of this basic configuration, just want to mention that TL max is what? TL max is what? 10 times log 10 1 plus 1 by 4 times m minus 1 m whole square this thing. So, since m typically we saw m, like if we consider diameter to be 350 mm or even if it is 300 mm and the port diameter is roughly say 50 mm. So, you are going to get m is equal to 300 by 50, this a square of course. So, 6 square, that is your 36. So, 1 by m is 1 by 36, which is very small compared to m. So, the idea is that we might want to drop the other term pertaining to 1 by m from the above expression to get a bit simplified expression, which is your m square by 4. So, this is an approximate expression for TL dome or TL max that we get from the analysis. So, this is what we are going to get. And what about the expression for TL minimum? That is of course 0, like we discussed now. So, using this estimate, one can very cleverly get a feel of the transmission loss. Actually, in many cases, if you want to do a further simplification, you could also perhaps try out dropping 1. You could also drop out 1 if m square by 4 is very small. You would get something like 10 times log m by 2 whole square to the base 10. So, this would become 20 and this would become 20 and this would be 10. So, TL dome 20 times log of m by 2. This is I would get rid of 10s understood. So, this is a even further simplified expression to get a very quick estimate of the maximum transmission loss that a simple expansion chamber can produce given the area ratio, given what will be the ratio of the cross section area of the chamber to that of the pipe or the port. What next we could study regarding the simple expansion chamber is the cascading of mufflers. There's many interesting elements. Actually, let me present to you some important slides where we probably can consider different elements, but we will probably analyze it a bit later. So, this is what it is. So, this presents to you, this is something that we have analyzed, a simple pipe or a pipe of uniform cross section, and this is something that we know, Helmholtz resonator. What we probably have not really seen so far are these elements. So, what are these? As the legend or as the figure caption suggests, this is an extension, extended inlet element, and this is an extended outlet element. So, basically, a simple expansion chamber is something like this, is not it? So, instead of the ports being flush mounted, if it is like this and if it is like this, then what happens? So, we have quarter wave resonators formed at the inlet and at outlet, and you will see that they will be instrumental, they will be they play the main role in uplifting the trough. We will probably have a look at it in the next lecture perhaps, but I guess it is important to just introduce these elements. And another one is of course a flow reversal expansion and flow reversal contraction, where the flow comes in here and it is forced to move like this. It produces a lot of back pressure though, but this cavity acts like a resonator, so does this one. Depending upon the diameter and this length, it might be a short cavity or long cavity. So, the wave propagation might be, we might cleverly choose a direction of wave propagation. Now, before we analyze such elements, I guess there are elements we might just want to consider doing a parametric analysis of the transmission loss of such chambers. I will very shortly present you that, and also talk about something like a cascading of transfer matrices. So, let me briefly talk about that. Let us say we have written a code in which a simple algorithm, I would not say even a code, functions are used in MATLAB. So, say TL underscore simple expansion chamber. We have just increased the font size, and what we are doing is writing a function. So, simple expansion chamber is just a name, and the function really wants 3 inputs. You could write your own function and have different inputs including sound speed, frequency range and so on. I have given it the option of choosing the port diameter, the diameter of the chamber and the length of the chamber. Note that the length of the inlet and outlet ports are right now sort of immaterial. Anechoic termination is imposed and there is nothing upstream, that is what we assume. Sound speed, so we could always comment things like this. So, alongside we will also try to learn some MATLAB hacks, and this is your frequency. So, 5 is the lower frequency and 3000 is the upper frequency. You could also do it something like 10, not an issue, and 5 is the increment. So, then you do with 10, 15, 20, 30, so on. And you right now we have non-dimensionalized the scale. Remember, this is the wave number and this is the square of the diameter ratio, or basically area expansion ratio. So, right now what we are doing is that using MATLAB to plot the analytically obtained transmission loss expression, which is this one. So, the idea is just to use that. So, once we do that, we probably will get, let us say the diameter is chosen as 50 and the expansion ratio, let us start with a smaller expansion ratio, that is given by, let us say it is 250 and the length continues to be 300. So, let us see what we get. We get this, and let me draw the grids, grid on for you or grid minor. We will get this thing. So, we could use the data point data tips here and get an estimate of the value. So, this is 3.14 approximately pi, because of the placement of the mouse or frequency resolution we are getting not exactly pi, but very close to pi. We can create another data point and continue to see that this is nearly 2 pi, 6.2 something, whatever it happens, and like this we will continue to have 3 pi, 4 pi and so on, and the maximum frequency occurs, domes occur when it is pi by 2, or that is close to 1.57 or 3 pi by 2, you know, and like this we can continue to do that. And notice the important values, 21.93, well 21.9 is the maximum TL, and what did we get when I showed to you the this thing, 20 times log m by 2. So, if you go to MATLAB and type 20 times log 10 and your m was what? M was 5 square, 250 divided by 50. So, 5 square is 25, 25 by 2, if you do that it is 21.93, bang on, and what we got is pretty much the same. So, this approximate thing gets you a very good result, and what I will do just to drive home the message how important the expansion ratio is, I have put this thing hold on, that is basically to hold the figure and plot it using a different color, which I am going to do now. So, let us say we have a slightly increased expansion ratio, which is like this. So, you see the transmission loss has gone up. So, what exactly was it? It was well, we can put a mouse here, 25.107. So, 20 times log, so 300 by 5, that is 6 square is 36. So, 25.10, and that is what we are what we are getting. Now, if you continue to do like this, let us say, let us consider another one final trial we probably can do. Let us say if you put 350, we are going to get higher transmission loss. Well, and the troughs continue to occur at the same frequency, so does the domes or things that are somewhere here where my mouse is. So, the idea is that by increasing the expansion chamber ratio, we are going to improve the transmission loss efficiency, we are going to get more attenuation. But one thing all this while we have not really bothered, and that is what bothers me. we have assumed only planar wave propagation so far. So, if you recall from our last lecture, it was the limit for the plane wave propagation, we will see all these things later, was k naught r naught is equal to 1.8412. Actually, for such a concentric simple expansion chamber with a concentric inlet and a concentric outlet, that is, you know, if this is a center line and this is your thing. So, this is all coaxial or concentric. For such a thing, actually azimuthal modes or circumferential modes will not propagate, only the radial modes propagate, and the first radial mode occurs at the frequency 3 point, I guess, if I am not wrong, it is probably 3.83 or something like that for a circular chamber. So, we can work out that, you know, and we are seeing the non-dimensional frequency axis. The point I am trying to make is that we can obviously calculate the frequency, cut on frequency based on this expression, at which the radial modes will start propagating. So, the nice beautiful dome trough pattern, this is the dome, this is the trough, dome and trough and so on. So, this beautiful dome trough pattern will break down just before the radial mode starts propagating, the 0 1 radial mode starts propagating. So, what frequency does it happen? It happens at a certain frequency which is given by the radius of the chamber. So, we can obviously show a line here which basically a vertical line to demarcate that beyond this frequency do not consider the planar wave propagation very seriously, because it will eventually break down. So, right now our world is only about planar wave propagation. So, let it be like this till we are confident in analyzing a large range of muffler elements like the ones we are discussing, extensions and resonators and all that, and with the understanding that the cut on frequency for the first higher order mode, that is the limit up to which these predictions, planar wave predictions, can be considered seriously, beyond which we should not. So, probably we have to wait till the time we consider 3D analytical formulation or analysis, and then we can consider all the 3D effects. But for now we will be sticking to 1D, and remember one thing, that so far although 3D techniques appear to be very attractive, they are obviously much more accurate than 1D, they are more realistic and so on. It is the 1D analysis that really helps you to understand the physics of the system. For example, before we end today's lecture, on a concluding note, let me just share something with you. So, we saw that you know, this is the chamber and it has a beautiful dome trough pattern. We would like to eliminate these troughs. So, by you know, basically considering protrusions or extensions of the inlet and outlet port within the chamber, we can actually eliminate this trough. How? Because these annular cavities act like quarter wave resonators, you know, these cavities at the inlet and the outlet. So, why are we so interested in this? Because if we can choose the resonance frequency of this cavity, let us say 1, such that k naught L1 cot k naught L1, the frequency corresponding to 0 impedance, remember this was the impedance. If this was tending to 0 at a certain frequency k naught, and the same frequency corresponds to where the chamber was showing its first trough. So, if these two frequencies can be matched, then the resonance peak due to this quarter wave resonator will annihilate or completely overcome the trough that is formed here. So, that the resulting pattern probably would be, so this is, if this is the expansion chamber thing, this thing would be something like this, and we can similarly tune the length of this to get this thing, and the third peak, third trough can also be uplifted. The idea is that resulting pattern would be a broadband attenuation using just a planar wave analysis and by wisely choosing the quarter wave resonator lengths based on planar wave propagation. But does that always help? Well, for a planar wave we are assuming these are the theoretical limits, and probably during the later parts of the course when we do analytical formulations and all that, we will see that these extensions based on the planar wave limit L by 2, L by 4, as we will see in the next class, aren't very well, they are useful to a certain extent, but they have to be supplemented by some end corrections or probably use of analytical models. Nevertheless, the 1D analysis has a special place as the beginning of the muffler analysis and helps in understanding the underlying physics, based on which we can do some further corrections like analytical 3D models or even numerical finite elements model based on actually a full 3D analysis or a mode matching techniques and all that. But for now, this week and the next week we will consider only planar wave analysis, at least for the next couple of weeks. So, before we move on to other topics. So, for now I will stop here and I will see you in the next class. Thanks.